All right, welcome to pages 70 through 72 in Lesson 10 of Unit 1, Algebra 2. All right, number 1 says a sequence is defined by 0, 3, and 2 times the previous term, n greater than 1. So we're going to write out the nth term for this. Well, first of all, let's write the sequence out. So we're starting with 3, because that's what this part says right here, is to start with 3. And then this says we just keep multiplying by 2 over and over again. So multiplying by 2 would give me 6, and then it would give me 12, and then 24, etc. So just doubling every time. So we need to write that so that we could go anywhere in the sequence and jump around. That's what the nth term means to do. So I'm going to write a function here. F of n is equal to, and then the first blank space is the starting point. So where are we starting? That's right, we're starting with 3. And what are we doing every time? Every time we're multiplying by a bunch of 2's. And we're going to do that a whole bunch of times. We're going to do that n times. So if n is 0, then we get the correct starting point. So if we put 0 in for n, it's 2 to the 0 power. And that would be 1, so we get 3. And then we ka-chunk to 1, we put 1 in for n. And then that would be 3 times 2, which is 6. So when we do this, we're saying that n is equal to 0, then n is equal to 1, then n is equal to 2, ... and then n is equal to whatever. And we can just put in any number of n into my function right here, and it'll jump to anywhere we want to go in the sequence. So that is the correct answer for number 1. Well, let's do the same thing down here for number 2, and I'll let you do the thing. I'll let you make the equation. So we'll write the recursive one together. We're going to do the recursive formula and the nth term. So this is geometric, which means I'm multiplying. Oh, I'm multiplying by 3, right? It goes from 20 to 60, so I'm multiplying by 3. So I have to define the first term. So the first term, f of 1, is equal to 20. And what are we doing every time? We're multiplying by 3. So I need to tell everybody that I'm multiplying by 3. F of n minus 1 means the previous term. And since I put a 1 over here for n, I'm going to say n is greater than or equal to 2. That's the way I've defined it. So you could have put f of 0 as 20, but I chose f of 1 for first term, second term. Now, we're going to write out the explicit formula. So I say f of n is equal to blank. So the starting amount, where am I starting? That's right, 20. So we put 20 in here. What are we multiplying by? 3. So we put a 3 here, and we do that a whole bunch of times. So we do n is greater than or equal to 1. So I guess I said I was going to have you do it, but I guess we kind of did it together. Now, n is greater than or equal to 1. So if I put 1 in for n, that's going to be 3, and then 3 times, the first term is 20. So I need to back the Mack truck up here a second, and I need to put a 1 right there. Because now when I put 1 in for n, it's 1 minus 1 is 0. 3 to the 0 power is 1, and I get 20. So that is going to generate the sequence as well and go anywhere that I want to in it. All right, so the next questions are all review questions, which are good. And it says geometric starts at 500, and then our growth factor is 0.6, and we're gonna make a graph of the first. So basically, what you need to do on this one is you're gonna make a graph here, okay? And the first term is 500, so you're gonna go up to 500. So I'm just gonna make a scale of 500 here, make it simple. So that would be, I don't know, 100, 200, 300, 400, 500. I think that'll work. Close enough for government work, right? So there's 1. So 1 is 500. Okay. So I'm going to make a table over here, and you're going to fill the table. And in first 5 terms, so n is 1, n is 2, n is 3, n is 4, n is 5. So 2, 3, 4, and 5. All right. So we're gonna make a little table here. So we're gonna do n is 1, 2, 3, 4, 5. And then we got f of n would be our terms, our answers. So 500 is the first one. So then you just keep multiplying by 0.6, the growth factor. Well, it's not growing. It's called a growth factor, but it's really going down because you're multiplying by something smaller than 1. So we're going to multiply by 0.6 to get this next answer. So I don't have a calculator right in front of me. I'm actually reclined on the couch and doing this. So you're going to multiply by 0.6 to get this answer, right? And then you're going to multiply by 0.6 to get the next answer. And you're going to do that, fill out the table, make the graph. All right, you can do that. Okay, that's the first page. And then we go to this page here. This is the review of section 1.8. Respond to each question, and arithmetic sequence has starting with 4 and then goes to 16. Explain how to show a value for a 15. Okay, so it starts with 4 and then 16, and it's arithmetic, right? So that means that it's going up by how much? Looks like 12. So if it's going up by 12, then we are going to the 12. We're going 12. 12 more would be 28, etc. And we could write that out and go all the way to 15, but I'm going to come up with a formula for this. So how do we do this? We did this on the previous page. So our starting amount is f of n. We're going to make a function here, and the first number is 4, and we're going to add on. We're adding a whole bunch of who? Adding a whole bunch of 12s. We're going to add on n of them. Now we say n is greater than or equal to 1. Now, does the formula work? If I put 1 in for n, does that give me 4? No. It's going to give me 16, which is the wrong one. So we got to back the Tonka truck up 1 space. There we go. So that's the formula for this. Now I can just put in 15. Oh, notice they used A, I used F. It's 6 of one, half a dozen the other. So f of 15, right? We're gonna put the 15 in for n and calculate what the answer is. So that's what you do on that one. Now we just did geometric, right? We did 2 geometrics in a row. Geometric multiplying by 2. This one was multiplying by 3. So we did 2 geometrics in a row. So you can do this one. Right? Now we're going to look at this geometrically. So we're starting with 4 and we're going to go to 16. Well, that's 4 times as much. So you're going to write the equation that works. So remember, how does the equation work? Oops. You have to have your starting amount right there, and then what you're multiplying by, and you're going to do it to the nth power, or it might be to the n minus 1, depending upon how you define it. So you have to make sure that it works. So write out the equation and then put in 16, and then it'll work. Oh, I see why they used A, because A would be for an arithmetic sequence, G they use for geometric. All right, this one is the section before, or we're cutting a piece of paper. And complete the table with the area of the paper in square inches after it's folded in half in time. So we're just going to fold it in half. So we fold it in half, there's half as much, right? So you just got to cut these in half, cut them in half, cut them in half, cut them in half. So when you cut it in half, what are you multiplying by? Well, you're multiplying by a half. So when we want the nth term here, A of n is equal to starting amount. It's 96, right? So you're going to fill this in by multiplying by halves. And we're going to multiply by half. We're going to do that to the nth power. Ooh, and goody goody, what's n? N is greater than or equal to 0. So when you put 0 in, you get half to the n power, or half to the 0 power, which is 1. So you get 96. So there's your formula. And you could even use that formula to fill those in. Now, what's a reasonable domain? What they're talking about here, this domain is your n values. So the domain is the domain is the n values, so n is 1, n is 2. So n means the number of folds. So you got 0 folds, 1, 2, 3 folds. So basically, how many times can you fold a piece of paper in half? That's what they mean by reasonable domain. Once you start folding the paper in half a bunch of times, it gets so thick you can't fold it in half anymore. So you can even do this by yourself. Take a piece of paper and fold it in half, and then fold it in half, and fold it in half, and fold it in half. See how many times you can do that, and then you'll know the domain. Okay, so this one here's a growing pattern. Describe the number of dots increases from stage 1 to 3. And then write the definition. So it's the number of dots. Is it geometric, arithmetic, or neither? Explain how you know. So I'm just going to write the numbers down. There's 2 dots, and then there's 4 dots, and then there are 8 dots, right? So then there would be 16. So it's definitely geometric because it's doubling. And I guess maybe I kind of, describe the number of dots increases. Well, it's doubling, so that's kind of what I would say there. It's doubling. Write a definition. Well, you can write you can write an equation for this like we've been doing, the starting amount and all that good stuff, so you can fill that in. And then we know that it's geometric. How do we know? Because it's doubling, right? And then the last one here, we are paper clips. So each paper clip weighs 0.5 grams, and a paper clip weighs 0.5 grams, and an empty envelope weighs 6.75 grams. So we're starting off with, see, n is 0 makes sense because there's no paper clips in there. That's just the weight of the envelope. Then you start adding in the paper clips. So each paper clip means as you go up, right, you're adding on 0.5, and then you're going to add another 0.5. All right, so Han, whatever, adds paper clips one at a time to empty envelope. Complete the table with the weight of the WN after N clips have been added. Okay, so we're filling out the table there. And then W of N, right, is what we're doing here. So N is the paper clips. Well, then they say, hey, what if it was W of 10.25? Does that make any sense? Well, W of 10 makes sense because you'd be adding in 10 paper clips. Now, unless you get out some pliers, it's kind of hard to add 10.25 paper clips. So that really doesn't make any sense, does it? All right, hopefully this has been helpful going through and figuring out the different problems here. So get that done, and woohoo, good for you.